So to extract a single ounce of gold from the ocean floor today, the standard operating procedure is, well, it's basically industrial scale vandalism.
Yeah, that's an accurate way to put it.
You essentially bring in a machine the size of a city block, scrape up acres of deep sea ecosystems, and, burn thousands of gallons of diesel just to pump thousands of tons of wet, freezing mud onto a surface ship.
Right.
And you do all of this, devastating the environment, just to sift out a few microscopic flakes of precious metal. I mean, imagine trying to perform delicate laser eye surgery, but the only tool you brought with you is a diesel-powered snowplow.
It's honestly a massive engineering failure when you view it from a systems perspective.
Definitely.
We're applying blunt mechanical trauma to this incredibly delicate environment because, well, historically, we just haven't had a better way to separate the target material from the surrounding medium right at the source.
But for you listening today, we have a deep dive that completely upends that archaic approach. We're unpacking a specific, highly technical patent application document 000002.
A really fascinating one.
And our mission today isn't just to summarize what this technology claims to do.
Yeah.
Because you requested it, we are going to examine the granular engineering implementation of exactly how it works.
Exactly.
This document suggests we could, leave the mud exactly where it is and use intelligently controlled invisible magnetic waves to pluck single flakes of conductive metal out of the dirt.
Right, all while the environment remains largely undisturbed.
Which sounds like sci-fi.
It does, but that focus on the engineering implementation is really what makes document 00000027 so compelling. I mean, if someone simply told you they wanted to use magnets to mine underwater, you might brush it off as a gimmick.
For sure.
But when you dive into the core thesis of this patent, it's detailing this unified, intelligent control architecture. It's an intricate web of electromagnetic probing, real-time dynamic mapping, and selective physical actuation.
Wow.
And it's all tied together in a closed-loop system.
I actually want to stop on that concept of a unified architecture.
Yeah.
Because, to go back to that surgery analogy, this patent is asking us to imagine a highly advanced robotic surgeon, right?
Yeah.
One that can diagnose the exact coordinates of a specific target, map the surrounding tissue in real time, and selectively extract the target without damaging the surrounding area.
Spot on.
Except, this surgeon is built to operate in the chaotic, high-pressure, freezing depths of the ocean. But here is my initial pushback when reading the source material.
Okay, let's hear it.
We have had underwater metal detectors for decades. We've had industrial electromagnets for over a century. So why is this patent treating the concept of finding and moving metal underwater like it's some completely new frontier in marine robotics? What makes the architecture itself the actual invention?
That gets right to the heart of the engineering challenge, because the novelty has absolutely nothing to do with the mere existence of an electromagnet. The breakthrough is the orchestration of the hardware and software in a highly hostile medium. See, traditionally, marine robotics has treated mapping and extraction as two entirely divorced phases.
Right, like totally separate teams.
Exactly. You deploy a sensor array to map an area, you take that data back to a surface vessel, analyze it, and then, days or weeks later, you send down a blind, dumb mechanical dredge to scoop up that entire general coordinate.
Which is so inefficient.
Incredibly. But this patent fuses those two realities. The sensor and the extractor are the exact same integrated hardware.
Oh, wow.
Yeah, operating simultaneously, making micro decisions in real time based on the immediate electrical feedback of the seabed.
So it's an event-driven loop rather than like a pre-planned schedule.
Precisely.
But to really grasp why a completely new system architecture is so desperately needed, we should probably spend some time looking at the engineering nightmare this patent is trying to solve. We have to dissect the brute force physics of current underwater mining.
We do, because the current state of the art is, frankly, archaic.
Yeah.
The industry relies heavily on dredging, hydraulic washing, and massive mechanical loosening. We're talking about giant cutter heads physically tearing into the seabed and massive suction pumps trying to create negative pressure environments to just lift everything up.
And when you look at the energy equation of that process, the inefficiency is staggering. I mean, you are spending millions of dollars in fuel, mostly just to move water and dirt.
Right. The industry calls it pulp. It's this slurry of water, mud, sand, and rock. And if you analyze the fluid dynamics of pumping pulp from a depth of, say, a few hundred meters up to a surface vessel, you're fighting immense physical challenges.
Because water is incredibly heavy.
Exactly. And when you introduce suspended solids into that water, the viscosity completely changes. The friction along the internal walls of the pipe skyrockets, and the energy required to maintain flow against gravity becomes exponential.
Not to mention the sheer bulk of it. You're lifting thousands of tons of this heavy pulp just to sift out a fraction of a percent of target material, like, platinum or gold.
Exactly.
It seems like the fundamental flaw is applying massive mechanical energy to the entire environment, rather than isolating the energy on the target itself.
That is the core inefficiency, the lack of selectivity. And, well, the secondary consequence of that lack of selectivity is catastrophic ecological damage.
Right.
When you use mechanical cutter heads and high-powered suction, you create massive turbidity.
Which are those enormous, choking clouds of suspended sediment. Right.
Right, and they can drift on ocean currents for miles. They completely suffocate delicate benthic ecosystems. They bury coral reefs, and they disrupt the entire local marine food web.
And the logic of the old method is just brutal. It's like demolishing your entire house, running the rubble through a giant sieve to find a lost wedding ring, and then dumping the rubble back on the lawn.
That's a perfect analogy.
Because you destroy the seabed, raise the mass, wash it, separate the metal, and then you have to dump that massive volume of waste dirt back into the ocean, which just creates a whole new plume of pollution as it falls.
It's a secondary ecological disaster. But the irony here, and perhaps the most baffling disconnect, is that our diagnostic technology is actually incredibly sophisticated.
Oh, total.
We have high-resolution side-scan sonar, autonomous underwater vehicles, laser scanning, advanced magnetometers. I mean, we can build beautiful maps of the ocean floor.
But once we find something on that beautiful high-tech map, we just send in the giant vacuum cleaner.
Right. The extraction hardware has completely failed to keep pace with the mapping software. We use a scalpel to find the anomaly and a sledgehammer to extract it.
Which perfectly sets the stage for the solution proposed in document 000027. So how do we stop bulldozing the house and just pick up the ring?
Right.
The patent's answer lies in what it calls a meticulously engineered adaptive intelligent control loop. And this completely rewrites the operational sequence, doesn't it? It's no longer destroy and sort.
No, not at all.
The new sequence is a highly controlled loop of probe, map, target, move, and verify.
Yeah, let's look at the control theory underlying that sequence, because the patent outlines a very specific 9-step operational flow.
Let's break it down.
Step 1 is positioning the underwater robotic complex. Step 2 is forming a diagnostic electromagnetic field. Step 3 is registering the electromagnetic response of the environment. Step 4 is detecting an anomaly within that response. Step 5 involves determining the specific parameters of that anomaly. Step 6 is updating the dynamic geological map.
Right, logging the data.
Exactly. Step 7 is selecting the appropriate mode of action based on the map. Step 8 is the physical actuation, actually moving the material using a specialized electromagnetic field. And finally, step 9 is verifying the result.
So if I'm looking at this from a software perspective, a traditional open-loop system is basically a washing machine, right?
Right.
It just runs its timer wash for 10 minutes, rinse for 5, regardless of how dirty the clothes actually are. But this 9-step process sounds way more like the architecture of an autonomous driving system. It's a closed loop. The results of every single physical interaction are fed back into the system to dictate the very next move.
The autonomous driving comparison is incredibly apt. An open-loop underwater system might be programmed with a rigid script like move forward 2 meters, dig for 20 seconds, move forward another 2 meters.
It's totally blind to its actual environment.
Completely blind. But the architecture in this patent is strictly event-driven.
So it's constantly making micro decisions based on the immediate feedback. Like
Yeah.
if it probes and detects a faint anomaly, it might decide on its own to pause, change the magnetic frequency, and probe again to get a clearer picture before deciding whether to extract it or just move on.
Exactly. Or if the signal suddenly shifts because the ocean current physically moved the target, the system recalculates the physical path in real time. And that requires an edge computing architecture where these decisions are made locally right there on the seabed.
Sure.
You cannot rely on sending the data up a tether to a surface ship, having a human look at a screen, and sending a command back down.
Right. The latency would make the system useless in a fluid environment.
Exactly. The robot treats the seabed not as a dead mass of dirt, but as a dynamic information physical environment. It's having a high-speed, continuous conversation with the geology using electromagnetic
The
waves.
idea that the mud is literally talking back to the robot is fascinating.
Hmm.
But for the robot to make any intelligent decisions, it first has to be able to hear and interpret that conversation clearly, right? It needs to see the target in all that chaos.
Right.
So let's unpack phase one of this architecture, electromagnetic probing.
So in the patent, this is referred to as the diagnostic mode. The robotic complex generates a primary diagnostic electromagnetic field. It then registers the electromagnetic response of the environment to hunt for conductive anomalies.
And here is where the electrical engineering gets incredibly intense. The source material doesn't just say it measures the response. It lists this entire symphony of electrical parameters.
It's very thorough.
Yeah. The system monitors changes in total impedance. It breaks that impedance down into active and reactive components. It measures equivalent inductance. It calculates the Q factor. It analyzes phase shifts between current and voltage. And it evaluates the spectral composition of the signal.
Yeah, it's a lot.
We really need to translate some of this for the listener because pointing a coil at mud and measuring reactive impedance sounds a bit like magic.
It does. To demystify it, we have to look at what impedance actually is in an alternating current circuit. Basically, impedance is the total opposition a circuit presents to an alternating current. But it's composed of two distinct phenomena, the active component and the reactive component.
I always think of the active component like friction. It's the standard resistance that just burns up energy as heat, like in a toaster.
That is a solid analogy. The active part dissipates energy, but the reactive part doesn't dissipate energy. It stores it and releases it, typically in a magnetic field or an electric field. Think of it like a spring.
Okay, a spring.
Right. So when the robot pulses an alternating electromagnetic field into the seabed and that field hits a highly conductive golden nugget, something fascinating happens based on Faraday's law of induction.
The changing magnetic field from the robot induces an electrical current inside the gold nugget itself.
Correct. Those are called eddy currents. And because moving electrical charges always create their own magnetic fields, the gold nugget suddenly generates a secondary magnetic field that pushes back against the robot's primary coil.
Wait, really? So the gold nugget acts like a phantom circuit that temporarily links up with the robot's hardware.
Exactly. And that phantom circuit dramatically alters the reactive impedance measured by the robot. It changes how the energy is stored and released in the field. But the system is also looking really closely at the phase shift.
Right, because in a normal empty circuit, the voltage and the current are moving in perfect harmony. But when you introduce that conductive metal anomaly, it delays the current slightly. It throws the rhythm off.
Yeah. If you imagine pushing someone on a swing, normally your push and their forward momentum are perfectly in phase. But if someone else grabs the swing for a split second as it moves, the timing of the swing's return is delayed.
Oh, I see.
That delay is the phase shift. And the robot's sensors are incredibly sensitive to these microsecond delays between the voltage and the current.
But the patent also specifically mentions measuring the Q factor or quality factor. How does that help identify the metal?
The Q factor essentially measures how underdamped a resonator is. It's the ratio of the energy stored in the oscillating resonator to the energy dissipated per cycle.
Okay, but in practical terms.
In practical terms for this robot, a high Q factor means the electromagnetic response has a very sharp, distinct peak at a specific frequency.
Like trying to tune a radio dial in a noisy room. A low Q factor would be a broad, staticky station that bleeds across the dial. But a high Q factor is a crystal clear signal locked on one exact frequency.
That's it, exactly. Which is vital when you're operating in the ocean. The ocean is incredibly noisy from an electromagnetic perspective. By analyzing the Q factor and the spectral composition, meaning how the signal breaks down across different frequencies, the system can filter out the noise.
Wow.
And it does this using single, multiple, or swept frequencies, utilizing both pulsed and sinusoidal signals.
Why the variety, though? Why not just use one continuous ping?
Because different target metals and even different sizes of the same metal resonate differently based on the frequency. High frequencies have a very short wavelength, meaning they provide incredible resolution for tiny objects, like a microscopic flake of platinum.
Right.
However, high frequencies suffer from the skin effect in conductive mediums like salt water. They attenuate quickly and don't penetrate deep into the mud.
Ah, so if a large gold nugget is buried a foot deep, the high-frequency ping just gets swallowed by the wet mud before it ever reaches the target.
Precisely. To find that deeper nugget, the system shifts to a low-frequency pulse. It doesn't have the granular resolution, but the longer wavelength penetrates the mud deeply to get a return signal. By sweeping through frequencies, the robot builds a comprehensive picture.
And all of this raw data, the phase shifts, the Q factors, the impedance changes across multiple frequencies, feeds into what the patent calls the dynamic geological map. Now, we should clarify for the listener, this isn't a topographical map on a computer monitor that a human is looking at.
No, no, it's not a visual interface at all. The dynamic geological map is an operational digital model. It is a digital twin of the seabed that exists entirely within the memory banks of the edge computing system on the robot.
A digital twin. It's building a mathematical replica of the physical world in real time. So what kind of parameters are actually living inside this database?
It logs the exact spatial coordinates of the anomaly in 3 dimensions. It logs the relative conductivity, which is crucial for determining the probable material type.
Okay.
But it also logs the environmental constraints, the density, the moisture content, and the baseline conductivity of the surrounding mud itself, because all of those factors skew the electromagnetic return signals.
And this leads to a massive engineering hurdle that I really have to push back on.
Sure.
Measuring a phase shift or a Q factor in a sterile, perfectly calibrated university laboratory is standard electrical engineering.
Yeah.
But this robot is doing it in an unpredictable, physically moving, freezing underwater slurry.
Right.
And the biggest issue, saltwater is inherently conductive. If the robot was looking for conductivity, wouldn't the entire ocean just look like one giant screaming anomaly?
Mhm.
How does the computational architecture differentiate a highly valuable platinum particle from, say, a pocket of incredibly salty, dense clay?
That is the ultimate bottleneck, and solving it is exactly why the intelligent control loop is the core of the patent. If the robot relied on absolute conductivity, it would be blinded by the salt water immediately. The architecture relies on comparative analysis and empirical data libraries.
So it has to zero out the environment, like
Hmm.
hitting the tare button on a digital scale before you weigh something to subtract the weight of the ball.
That is an excellent way to conceptualize it. The system is constantly taking background readings as it moves. It establishes a localized baseline of what empty saltwater and mud look like at that exact temperature, pressure, and salinity.
Oh, that makes sense.
Yeah, so when it fires a diagnostic pulse, it isn't looking for raw conductivity. It's looking for the delta, the sudden sharp change against that specific localized background.
But even a pocket of dense, salty clay would register a delta against regular mud, right?
It would, and that is where the complex parameters come in. A pocket of salty clay will change the active impedance, but it generally will not produce the sharp, high Q factor phase shift and the massive spike in reactive impedance that a solid, crystalline piece of metal will.
Interesting.
The system cross-references the incoming delta against massive empirical data libraries stored on its drives.
So it literally has a library of electromagnetic fingerprints. It compares the live ping to a profile of platinum, a profile of iron, a profile of wet clay, filters out the background tearaway to the ocean, and calculates a probability score.
Exactly. And it does all of this mathematical filtering and comparative analysis in fractions of a second while navigating underwater currents.
Truly staggering computational edge processing. But here's where this deep dive really accelerates, because finding the gold is only half the battle. Once the digital twin has isolated the exact coordinates of the target and confirmed its material probability, the robot doesn't reach down with a mechanical claw. The system has to shift its entire identity from being a passive diagnostic sensor to an active physical actuator.
It does.
It has to actually move the metal. Let's dig into phase 2, the actuator and the electromagnetic conveyor belt.
This transition is where we move from the virtual world of mapping back into the physical world of kinetic extraction. The patent outlines that the system forms a controlled electromagnetic field with a moving interaction zone to selectively move the conductive material toward a collection zone.
Let's focus on the hardware reality of this. The document refers to cascades of electromagnetic action. What does the physical architecture actually look like on the hull of this robot?
We are talking about extensive arrays of electromagnetic coils. The patent specifies linear stators, multisectional windings, electromagnetic matrices, and planar coil arrays.
Okay, that's a lot of terminology.
Just imagine the belly of this autonomous submarine, or a specialized working nose, tiled with a dense grid of heavily insulated wire coils.
Like the heat-resistant tiles on the underside of a space shuttle. But each tile is an independent electromagnet.
Yes. Now, the physics of how this grid actually moves a piece of metal is where it gets counterintuitive. We have to remember that our primary target metals, gold, platinum, palladium, are non-ferromagnetic.
Right. If you take a standard refrigerator magnet and hold it over a gold wedding ring, absolutely nothing happens. There's zero attraction. So how is an electromagnetic field supposed to physically pull a gold nugget out of the mud?
It relies heavily on induction and electrodynamics, specifically the Lorentz force. We touched on Faraday's law during the diagnostic phase, how a changing magnetic field induces eddy currents in the gold.
Yeah.
During the actuation phase, the system uses that exact same principle, but cranks the power up exponentially,
So it fires a massive, rapidly varying, alternating magnetic field from one of the coils into the gold nugget.
which induces massive electrical currents swirling inside the non-magnetic gold. Now, because there's an active electrical current flowing inside the nugget generates a very strong secondary magnetic field.
Wait, so the system weaponizes the gold's own high conductivity to temporarily turn the non-magnetic nugget into an electromagnet.
Exactly. And now that the gold nugget is projecting its own magnetic field, that field interacts with the primary magnetic field still coming from the robot's coil.
Wow.
The physical force generated by the interaction of these two magnetic fields is the electrodynamic force. By carefully manipulating the frequency, the phase angle, and the amplitude of the primary field, the intelligent control loop can dictate whether those two fields repel each other or attract each other.
That is brilliant physics. It's similar to that classic university physics demonstration where a professor drops a strong neodymium magnet down a hollow copper pipe.
Right.
The magnet doesn't free fall, it floats down in slow motion because the falling magnet induces eddy currents in the copper pipe, which create a magnetic field that physically pushes back against gravity.
It is the exact same underlying mechanism, but engineered for highly targeted, localized extraction. The robot's primary field literally grabs the induced field of the nugget and pulls it through the mud.
Incredible.
But the patent takes it a step further. It isn't enough to just nudge the gold out of the mud. The robot needs to transport it along the hole to a collection bin. This requires what the document calls the transfer between cascades.
The electromagnetic conveyor belt. How does the system orchestrate that transfer across the grid of coils we discussed?
Let's visualize that grid of coils on the hull. The intelligent loop powers up coil A. This induces the massive field, creates the Lorentz force, and pulls the gold nugget up out of the mud and towards coil A.
Okay.
But milliseconds before the nugget actually impacts coil A, the control system kills the power to coil A and instantly energizes adjacent coil B, but with a highly specific phase shift.
So the magnetic attraction seamlessly shifts. The nugget is now being pulled sideways toward coil B.
And right before it hits B, B shuts down and C powers up. By meticulously synchronizing the phase shifts, alternating the frequencies, and sequencing the massive power dumps across the adjacent coils, the robot creates a traveling magnetic wave across its hull.
The best way I can visualize this is crowd surfing at a concert.
Oh, I like that.
The gold nugget is the surfer, and the individuals switching electromagnetic coils in the grid are the hands of the crowd. The hands aren't running across the floor. They stay in their fixed positions. They just pop up, apply upward and lateral force at the exact right millisecond, and then drop back down, perfectly synchronized, to pass the surfer along a specific controlled path all the way to the stage, or in this case, the internal collection bin.
The crowd surfing analogy perfectly captures the mechanics of a traveling wave. There are zero moving mechanical parts on the exterior of the robot. The hands are the individual cascades of electromagnetic action, and the complex choreography is managed entirely by the software of the adaptive intelligent loop.
But wait, if you have a massive grid of heavy-duty coils to physically pull heavy gold nuggets through thick mud, and a completely separate array of highly delicate antennas to listen for the tiny phase shifts during the diagnostic phase, wouldn't the hull of this submarine need to be the size of a football field to fit all this hardware?
You would think so.
How do they physically package this onto a compact underwater drone?
This brings us to what is arguably the most elegant and most difficult engineering trick in the entire patent. The hands in that crowd, the coils passing the surfer along, are the exact same hands that found the surfer in the first place.
Wait, really?
Yes. The patent explicitly claims the use of a shared electromagnetic executive module for both probing and actuation.
So they're using the exact same physical coil to act as a delicate diagnostic antenna and the massive actuator tractor beam. Why is that shared architecture such a massive advantage? Why not just put the sensors on the front bumper and the big magnets on the back bumper?
Because in fluid dynamics, spatial error is a killer. If your sensor array is on the nose of the robot and your actuator array is on the belly, you introduce a physical distance and a time delay between detection and action.
Ah,
In a chaotic environment like a turbulent underwater slurry, the medium is constantly moving.
right. If you ping a gold flake with the front bumper, by the time the submarine moves forward to align the back bumper over those coordinates, the ocean current might have swept the flake 3 feet to the left.
Exactly.
Right.
The target isn't going to just sit there waiting for the actuator to arrive.
Right.
So, by using the exact same physical coil to sense the impedance change, and then immediately utilizing that same coil to generate the Lorentz force to pull the particle, you completely eliminate spatial displacement errors. The point of detection is the exact literal point of actuation. There is zero physical offset.
That drastically reduces the calibration nightmare, too. You don't have to write complex software to align two different sensor grids. The eye is the hand.
The eye is the hand, is a great way to put it. It also eliminates latency. You aren't processing coordinates, passing them across a data bus to a different hardware module, and waiting for mechanical alignment.
But from an electrical engineering standpoint, this sounds impossible.
It's definitely challenging.
You mentioned earlier that the sensing mode uses high frequencies to detect delicate phase shifts, which requires very low power. But the actuating mode needs to induce massive eddy currents to physically shove heavy metal through dense mud, which requires massive power and usually much lower frequencies. How can a single piece of copper wire act as both a whisper-sensitive antenna and a high-voltage bulldozer?
The engineering specs behind this hardware flexibility rely heavily on advanced materials science and bleeding-edge power electronics. Let's start with the physical coils themselves. The patent specifies the use of Litz wire.
Litz wire. What is the physical structure of that, and why is it necessary?
Litz wire is a highly specialized type of multi-stranded cable. Instead of one thick, solid copper core, Litz wire is constructed from hundreds, sometimes thousands, of individually insulated microscopic copper wires that are intricately twisted and braided together in a very specific geometric pattern.
Why go through the incredible manufacturing difficulty of braiding thousands of insulated microscopic wires? Why not just use a standard thick copper cable to carry the massive current needed for the actuator?
To combat a phenomenon known as the skin effect. When you run a high-frequency alternating current like the kind required for the diagnostic probing phase, the current does not flow evenly through the entire cross-section of the wire.
Right.
The alternating magnetic fields generated inside the wire force the electrons to the outer perimeter, or the skin, of the conductor.
So if you use a solid thick wire at high frequencies, the entire center of the wire is basically dead weight.
It is worse than dead weight. Because the electrons are crammed into a tiny outer layer, the effective resistance of the wire skyrockets. The wire heats up massively, you lose tremendous efficiency, and you completely degrade the delicate high-frequency diagnostic signal.
Wow.
Litz wire solves this. By using thousands of tiny wires, you create massive amounts of skin surface area throughout the entire cross-section of the cable. This allows the coil to act as an incredibly efficient, highly sensitive antenna for the high-frequency probing phase.
Okay, so the Litz wire makes the dual use possible from a physical standpoint. But how does the system actually switch the power? It has to jump from a low-voltage diagnostic ping to a massive low-frequency power pulse instantly.
That is where solid-state switching comes in. The patent highlights the use of advanced semiconductor power electronics like MOSFETs, IGBTs, NAND, which is gallium nitride or Sanctrec, silicon carbide transistors.
We hear a lot about gallium nitride and silicon carbide in the context of advanced electric vehicle inverters or fast chargers. What makes them so critical for the submarine?
It comes down to band gap engineering. Traditional silicon transistors would literally melt if you asked them to handle the voltages required for the actuator phase while switching at the speeds required for the diagnostic phase.
That makes sense.
Gallium nitride and silicon carbide are wide bandgap semiconductors. They have much higher electron mobility and thermal conductivity. They can handle incredibly high voltages and massive currents without breaking a sweat, but crucially, they can transition from an off state to an on state in fractions of a microsecond.
So the intelligent control system uses these GaN or CTAS switches to dynamically rewrite the architecture of the coils on the fly.
Exactly. The solid-state switches can take a group of Litz wire coils that are currently wired in series to create a delicate, highly tuned sensing antenna, and in a microsecond, snap them into a parallel configuration to dump a massive power pulse that physically shoves the metal.
That is software-defined hardware taken to the absolute extreme. The physical coil on the hull of the submarine doesn't move a millimeter, but its entire electrical identity, its resistance, its function is rewritten millions of times a second.
Yeah, the system can ping a high-frequency diagnostic pulse, detect the impedance shift of a gold nugget, slam the solid-state switches into parallel power mode, fire a massive low-frequency Lorentz pulse to pull the nugget 1 inch, slam the switches back into series diagnostic mode, ping again to verify the nugget actually moved, and repeat the cycle.
And this entire transition happens in the blink of an eye.
Exactly.
This incredible hardware flexibility, the ability to be a sensor and an actuator simultaneously, is what allows the system to be deployed in incredibly diverse and physically punishing environments. Which leads us to the implementation scenarios detailed in the patent, because the seabed is not a uniform environment.
Precisely. Because the extraction mechanism relies entirely on programmable electromagnetic fields and requires no moving physical scoops, the physical configuration of the robot can adapt. The patent outlines designs where the shared electromagnetic module is mounted on the nose of a rover, the stern bottom mounted on a sled, or even integrated into a partially submerged apparatus.
Let's explore the first scenario the document outlines. Working with a flow, or what the industry calls a pulp.
This is a scenario where there's already a slurry of moving mud and water. This could be a natural, fast-moving riverbed, or it could be a scenario where the robot utilizes a mild propulsion system to stir up a highly localized, controlled flow of the top layer sediment.
Right.
In this environment, the engineering challenge changes. The electromagnetic field doesn't need to do the heavy kinetic lifting of pulling the gold from a dead stop all the way to a bin. The fluid dynamics of the water are already providing the kinetic energy to move the material.
So the water's moving the gold, the sand, and the mud past the robot. What is the role of the electromagnetic field then?
It acts as an incredibly precise deflector shield. As the slurry rushes past the Litzwire sensor grid, the system runs its diagnostic loop and identifies the specific coordinate of a gold flake in the flow in real time. But instead of trying to grab it, the system fires a very quick, highly localized lateral electromagnetic pulse.
It just nudges the trajectory of the gold flake sideways.
Exactly. It uses a burst of Lorentz force to push the conductive gold laterally, deflecting it out of the main waste stream and into a collection side channel or hopper.
It's like a bouncer at an exclusive club standing by a fast-moving crowd. The bouncer doesn't try to stop the crowd. They just reach in, identify the VIP, and gently pull them into a side door while the rest of the crowd just keeps walking right past.
That's brilliant. And that means the massive volume of waste dirt, the sand, the mud, the non-conductive rock, simply continues on its natural path and settles immediately back onto the seabed directly behind the robot. You aren't fighting the momentum of the environment, you are just using minimal energy to filter it with invisible magnetic nudges.
That is incredibly elegant and energy efficient. But what about the second scenario, working without a flow? Say the robot is just hovering over a solid, static patch of deep ocean clay.
In a static environment, the system relies heavily on that full electromagnetic conveyor belt we discussed. The robot positions itself directly over a solid anomaly. It pings the ground, maps the target's depth and parameters, and then uses a focused high-power sequence to pull the target straight up, vertically, out of the top layer of the seabed.
Pulling it straight through the mud.
Right. It pulls the metal through the stationary mud, up to the hull, and then walks it along the cascaded coils to the internal bin.
And the most important takeaway here is that it achieves this without pumping any water. No massive vacuum systems, no gigantic plumes of silt choking out the coral reefs. It magnetically plucks the needle out of the haystack and leaves the hay completely undisturbed.
The waste dirt stays exactly where it belongs, which paves the way for arguably the most revolutionary operational deployment of this technology, the sub-ice and Arctic application.
The logistics of Arctic mining are notoriously brutal. Current extraction requires massive surface vessels.
You simply cannot operate a massive surface dredging ship with a giant pipe reaching to the ocean floor if the surface of the ocean is covered in 10 feet of solid, shifting Arctic sea ice.
Right.
Obviously. Traditional dredging in the Arctic is a logistical nightmare. You require heavy icebreakers, you are limited to an incredibly short summer operational window, The physical danger to the crew is immense, and the environmental regulations are rightfully incredibly strict to protect the fragile ecosystem.
But if you remove the fundamental requirement of pumping mud to the surface, the entire architecture changes.
Radically. Because this patented architecture performs the sensing, the physical extraction, and the separation locally on the seabed, the entire system can be miniaturized. It doesn't need a massive diesel power plant to run vacuum pumps. This technology can be integrated entirely into an autonomous underwater vehicle, an AUV.
An autonomous drone submarine operating under the ice.
Yes, you deploy the AUV under the Arctic ice sheet. It requires no surface support ship. It requires no physical tether or pipe to the surface.
Wow.
Powered by high-density batteries, it can operate autonomously for months at a time. It quietly glides just above the seabed, pinging the mud, mapping the geology, magnetically plucking pure precious metals, storing them in a small internal payload bay, and leaving the Arctic environment completely untouched.
Just visualize the contrast. The old paradigm.
Yeah.
A massive diesel-belching surface ship, relying on icebreakers, dropping mechanical cutter heads, destroying the seabed and creating massive pollution plumes.
Right.
The new paradigm under document 000027, a sleek, silent AUV gliding in the pitch black under a frozen ocean using intelligent magnetic waves to gently extract single particles of platinum, making micro-decisions every millisecond. It really sounds like science fiction.
It does, but it is entirely grounded in demonstrable control theory, advanced material science, and fluid dynamics.
Now, I do want to bring up one caveat I found in the source document. The patent does concede that mechanical loosening might still be required in certain scenarios. Does that admission defeat the entire purpose? Are we just bringing a mechanical bulldozer down there anyway?
It is a valid concern, but we have to look at the engineering context of that mechanical loosening. The patent acknowledges that the seabed is not always soft mud. Sometimes you encounter heavily compacted sedimentary layers or cemented rock.
Right.
In those specific geologies, the electromagnetic Lorentz force, while strong, is not sufficient to physically shatter solid rock to free a metal particle trapped inside. You must apply mechanical preparation.
So they do have to break the rock up.
They do, but the critical distinction is what happens after the rock is broken.
Yeah.
In the traditional dredging paradigm, you shatter the rock with a cutter head, and then you vacuum up the entire volume of shattered rock, pump it hundreds of meters to the surface, and mechanically sift it on a ship.
Yeah, moving all that weight.
With this intelligent architecture, the loosening is strictly localized preparation. The robot might deploy an ultrasonic cavitation emitter or a highly targeted mechanical ripper just to fracture the top few inches of the seabed directly over the target. But the actual extraction, the removal of the target material, remains entirely selective and electromagnetically driven.
Ah, I see. So you fracture the rock, but you leave the shattered rock right there on the bottom. You pass the Litz wire coil grid over the fractured area, induce the eddy currents, magnetically pull the gold out of the rubble, and leave the thousands of tons of broken rock exactly where it is.
Exactly. You are still completely bypassing the need to transport bulk waste through the water column. You avoid the massive energy expenditure and the secondary pollution of dumping the waste back down. The core philosophy of the architecture holds up even in difficult geologies.
It becomes incredibly clear that document 000027 is not just a patent for a new tool to bolt onto an existing submarine. It is a completely new philosophy for how we interact with natural resources. It is a foundational paradigm shift in marine engineering.
It truly is. Which brings us to the ultimate summary of the architecture. This patent protects a framework for adaptive intelligent control for underwater electromagnetic interaction. It represents the evolutionary leap from blind, destructive kinetic force to closed-loop, data-driven, highly localized electromagnetic manipulation.
Let's crystallize that operational sequence one more time because it is the defining breakthrough. The architecture relies on an edge computing loop. Probe the environment with high-frequency signals. Build a real-time digital twin of the geology. Decide on the optimal extraction parameters based on localized empirical data. Instantly reconfigure the hardware to actuate a powerful, low-frequency magnetic wave to move only the conductive target, and verify the extraction before moving to the next coordinate.
And this blueprint achieves two historically contradictory goals simultaneously. It dramatically mitigates ecological destruction by eliminating the turbidity plumes and mass excavation associated with mechanical dredging. And it exponentially increases economic efficiency by leaving the waste material exactly where it is, circumventing the immense energetic and logistical costs of transporting useless mud.
It is a rare scenario where industry and ecology both win, made possible purely through brilliant systems engineering, Litz wire, and gallium nitride transistors. But before we wrap up this deep dive, I want to leave you, the listener, with a broader thought experiment, a question that goes far beyond mining the ocean floor.
Let's extrapolate the architecture.
Think about the core engineering loop we just spent this time unpacking. We've designed a localized, closed-loop system that utilizes the exact same physical hardware module to digitally map a chaotic, fluid environment and then instantaneously reconfigures its electrical properties to manipulate physical matter on a granular level using nothing but programmable electromagnetic fields.
A software-defined sensor-actuator feedback loop operating in a fluid medium.
Right. So where else in the world do we have chaotic fluid mediums that require highly localized, non-destructive extraction? What happens if we take this same listen map and magnetically move architecture and shrink it down to the micro scale? Could this exact same systems engineering be applied in medicine?
That is a fascinating trajectory. If you scale the physical coils down to the micro level and drastically increase the frequency sensitivity of the diagnostic pings.
Could you engineer a micro-robotic architecture?
Yeah.
A medical device that utilizes this exact same intelligent loop to detect and magnetically extract heavy metal toxins from the human bloodstream, completely eliminating the need for invasive surgery or broad-spectrum chelation therapy.
Oh, wow.
Could a microarray flow through a vein, use microscopic Litzwire coils to ping for lead or mercury anomalies in the blood, build a real-time digital twin of the toxin distribution in that specific artery, and then instantly switch to a phase-shifted actuator mode to magnetically pull those toxic particles out of the blood plasma and into a collection shunt?
The underlying physics and the control theory algorithms would be remarkably analogous. You are simply swapping the fluid dynamics of ocean mud for the fluid dynamics and viscosity of human blood.
Right.
The adaptive intelligent loop, the requirement to sense, filter background noise, target, and actuate without damaging the surrounding environment, remains exactly the same.
From extracting platinum under the freezing high-pressure ice of the Arctic Ocean floor to potentially extracting toxic heavy metals from the microscopic vessels of the human circulatory system. That is the true power of revolutionary engineering architecture. I want to sincerely thank you, the learner, for bringing document 000027 to the table. This incredibly dense, highly technical source material is exactly the kind of mind-expanding engineering we love to dissect. Keep hunting down these amazing sources for our next deep dive. Keep questioning the established paradigms, and we will catch you next time.